So I want to go over the example that we started in class. I figured I would just start it again just so that you guys kind of had the beginning process here. So we're looking to optimize volume. So we have our open box. We know that its dimensions are 16 by 30. So I'm going to draw myself a little sketch here again. So my length's 30 inches, my width 16 inches, and we know that we want to get rid of the corners. So I'm going to go ahead and dot those lines in, and we know that those dimensions are what we're looking for. We don't know how big these corners are that we want to cut out. Okay, so what we know is we know that we are looking to maximize volume. And we know that the volume of a rectangular box would be length times width times height. And we said that when these corners are gone, our length would be 30 minus 2x. Our width would be 16 minus 2x, and our height would just be x. So we said that we were able to take these three dimensions, make a volume formula from them. So x times 30 minus 2x times 16 minus 2x. And probably the best way to go about doing this is, again, to FOIL these two out and then distribute in your x afterwards. So this gave us 480 minus 92x and then plus 4x squared. And then when we distributed it out and then wrote in standard form, this gave us 4x cubed minus 92x squared and then plus 480x. Okay. So when we go to find our critical numbers, or when we go to take the derivative of this and then set it equal to 0, we're going to end up with a couple of x values. What we really hadn't touched base about yet was these dimensions. So we know that the dimensions of any sort of like box or area or length or width or whatever the dimension is, we need them to be positive. So we have to make sure that whatever the x values that we end up getting when we take our derivative and set it equal to 0, they're going to make sure that these lengths, widths, and heights are going to be positive. So we have to be a little bit careful about our restriction. So we need to make sure that the length of our box is greater than 0. So if we plug in the length 30 minus 2x, this is going to tell us that 30 must be greater than 2x, which is going to tell us that 15 must be greater than x, or in other words, x is less than 15. So we also have to do the same thing with our width. So not only do we have to make sure that our length is positive in value, but we also have to make sure that our width is positive. So our width would be 16 minus 2x. That would give us 16 is greater than 2x, which would be 8 is greater than x, or what that's telling us is x is less than 8. And then we also have to make sure that the height is positive. So that's telling us that x is greater than 0. So we have three different things going on here. We know x has to be greater than 0, x has to be less than 15, and x has to be less than 8. So if we kind of combine these into one sort of like domain restriction, we know that it's obviously got to be greater than 0. So I'm going to start writing it as a compound inequality. We know that x has to be greater than 0, and it has to be less than something. Is it less than 15 or is it less than 8? Well, let's pick a value somewhere in between there. What if I said x was 10? So what if I ended up getting, like, setting this equal to 0, getting a critical number of 10? Well, if I plug 10 back in here, the height could be 10. That's a positive value. But if I plug 10 back in here to the width, that's going to give me 16 minus 2 times 10, which would be 16 minus 20. That would give me a width that's a negative length. So if I plugged in 10 here, 30 minus 2 times 10 would be 30 minus 20, which would give me a positive length. But the problem is this width. So to restrict our domain, we actually have to use 8 as our greatest number. Because if I plugged in anything greater than 8 into the width, that would give me a negative length, which I can't have. So in this case, our domain of this particular problem is going to be somewhere in between 0 and 8. And it could be including 8. So my domain, actually, I wouldn't be able to be including 8 because if I plugged in an 8 here, that would give you a 0. So somewhere in between 0 and 8. So that's going to be important over here because now that we want to take the derivative of this to figure out where our maxes are happening, let's go ahead and do that. So let's do a v prime. That would be 12x squared minus 184x and then plus 480. I want to set this equal to 0. And I'm also noticing that these numbers definitely have a GCF in there. I believe the GCF is 4 here. So 3x squared minus 46x and then plus 120. This is a factorable quadratic, so I'm going to go ahead and factor that out. So that would be, let's see, set up my 3x and my x. So I believe that's a negative 12 over here and a negative 10 over here. So if I set those equal to 0, that's going to give me a critical number of 10/3 and a critical number of 12. So if I'm thinking about what fits my domain restrictions here, well, if I divide 10 by 3, that's going to get me something in between those values. That's about 3 1/3. And then 12, well, that's above this domain that I'm talking about, because if I took 12 and substitute it back into the width, 16 minus 2 times 12 would be 16 minus 24, which would give me a negative width. So in this case, I actually don't want to include this as a critical number because that exceeds what I can substitute in to get a length or width or height or whatever of a positive value. So this one doesn't work, since if I use the width formula, that would give me 16 minus 2 times 12, which would be 16 minus 24, which would be negative 8. So that does not work. So this is going to be my only maximum value here. So I want to go ahead and use the second derivative test to confirm. So I know this is where my f prime is equal to 0. So my f double prime here, or my v double prime, I should say, I want to take the derivative of this. So that would be 24x minus 184. And what I want to do, this derivative is a little bit different than the ones that we went over in class. Since this one still has an x in it, I want to actually put 10/3 in it to confirm that when I put that 10/3 in, I end up getting something here that would be negative. So I'm going to do v double prime of 10/3. So 24 times 10/3 minus 184. I think this gives me 80 minus 184, which gives me a obviously negative number, negative 104. So if my v double prime is less than 0, that's telling me that my graph is concave down, which means that this is a max point. So x is equal to 10/3 is in fact a max. And this is actually going to help me answer my question here. If I go back up to see what the question's asking me, it's saying what size should the squares be to obtain a box with the largest volume? Well, this x, remember, is representing our height. So this is the dimension of the squares that we're actually cutting out of the side of the box. So this 10/3 is actually our answer here. So I'm going to say the squares would be 10/3 inches by 10/3 inches. If it was asking me for what my maximum volume was, then I would want to go ahead and take this x and actually find out what my dimensions would be. So the height would be 10/3, the width would be 16 minus 2 times 10/3, the length would be 30 minus 2 times 10/3, and then I would want to multiply all those together to get what the volume would be. But in this case, it's just asking us for the size of the squares. So that's it for that question. Now you can go ahead and try the last question on your homework and let me know if you have any questions.